We've been considering different types of intermolecular forces and how they relate to water as a solvent. We now want to consider a special type of interaction known as hydrogen bonding. Although not unique to water, it is perhaps best exemplified in water. Hydrogen bonds result from non-covalent attractions between dipoles. One of these dipoles is carried by a donor and one is carried by an acceptor. The positive dipole is a hydrogen atom covalently bonded to the electronegative donor. The hydrogen bond acceptor is also electronegative and has a lone pair of electrons available to share in forming the bond. A linear alignment of the atoms within the bond, as illustrated on the left, results in greater overlap of the van der Waals radii, a shorter bond length, and therefore a stronger bond. A nonlinear alignment results in a weaker bond, as illustrated on the right. As you can see from the figure on the slide, both hydrogen fluoride and ammonia can form hydrogen bonds, each having in its structure both the required donor and the acceptor atoms. In the case of hydrogen fluoride, each molecule has one hydrogen bond donor and three acceptors, the three lone pairs of fluorine. Each ammonia molecule has three donors and only one acceptor on the nitrogen atom. However, in the case of water, in the center of our figure, it seems optimized for hydrogen bonding, with two acceptors in the two lone pairs of oxygen and two donors. This makes it unique in being able to form an optimum network of hydrogen-bonded molecules. Another factor that contributes to the unique bonding properties of water has to do with its tetrahedral arrangement around the oxygen atom. Due to the two lone pairs on the oxygen atom, the bond angles are around 104 degrees. In solid water, the hydrogen bonding network is more restricted, leading to a more open, less densely packed arrangement than in liquid water. Therefore, water is one of the few compounds on Earth whose solid form is less dense than the liquid form. This is why ice floats on oceans and in our water glasses. Hydrogen bonds are relatively weak as compared to covalent bonds, on the order of only about 20 kilojoules per mole. Nevertheless, they confer on water an unusually high boiling point and melting point as compared to molecules of similar size like ammonia and methane. Again, we see water is most unique. Water can hydrogen bond not only with itself, but also with other polar molecules. It can be an acceptor to an alcohol group, illustrated on the left, a donor to a ketone group in the center, and an acceptor to an amine group on the right. One of the primary reasons for the solubility of polar compounds in water is their ability to form hydrogen bonds with water. Hydrogen bonding is also an important factor in stabilizing the three-dimensional structures of other biomolecules, like proteins and DNA. As we consider other topics in biochemistry, we will see that hydrogen bonds play a key role in forming and stabilizing many cellular structures.